Hello friends, Savitribai Phule, Pune University, TYBSc Physics, Course 1, that is Mathematical Methods of Physics. There are 4 chapters in this course. Out of that, today we are going to discuss few important multiple choice questions on the topic. Title is Curvilinear Coordinate System. Now we have been introduced to different types of coordinate system such as Cartesian, spherical polar coordinate system, cylindrical coordinate system, and so on. All these systems can be a part of one of the system, generalized coordinate system, which is called as orthogonal curvilinear coordinate systems. So in the theory of this system, we come across different types of parameters like coordinate axis, coordinates, then coordinate plane. Then we go for different types of scale factors, metric coefficients, and once we understand all these things, then we can go for several geometrical as well as calculus parameters such as length element, surface element, volume element, as well as gradient of the scalar point function, divergence of vector point function, curl of vector point function, and Laplacian of the scalar point function. So this entire chapter is based upon these few definitions, and therefore the MCQs which we are discussing here, they are also based upon this type of concepts what we have studied in this particular chapter 1, that is curvilinear coordinate system. Now let's come to the questions one by one. In the Cartesian coordinate system, the coordinate surfaces and coordinate lines are dash dash to each other. 4 options are given: A parallel, B anti-parallel, C perpendicular, and D tangent. So you have drawn this diagram earlier. We show in this case of Cartesian coordinate system, there are 3 axes: x-axis, this is y-axis, and this is the z-axis, or you can take any orientation. So this plane here, the plane which is made by y and x, this plane is having z is equal to 0. So this is called as coordinate surface z is equal to 0. This is coordinate surface y is equal to 0, and this is coordinate surface x is equal to 0. All these 3 surfaces are perpendicular to each other, and where these 2 surfaces intersect each other, we get that is called as coordinate line. So this coordinate line and coordinate surfaces, these are formed, and these are found to be perpendicular to each other, and therefore answer C is the correct answer here. So in Cartesian coordinate system, the coordinate surfaces x equal to 0, y is equal to 0, z is equal to 0, and coordinate lines are perpendicular to each other. So this coordinate line, x is perpendicular to y, x is perpendicular to z, y is perpendicular to x-axis, as well as it is perpendicular to z-axis, and like that. That's why correct answer of this question 1 is C, perpendicular. Now question 2. In the spherical polar coordinate system, theta is equal to constant. The coordinate system dash dash with its vertex at origin. So we have to go for a coordinate surfaces. Now in case of Cartesian coordinate system, we draw, this is the xyz coordinate system. Okay, name all this. This is x, this is y, and this is z. And here any point P, it can be taken as xyz, and whereas this point can be drawn at a distance of r. Now take a intercept of this on this plane. So you will get this to be r. This angle is taken to be theta, angle with the z-axis is taken to be theta, and this angle made by its projection over here, this is given to be phi. Now once we go for these values of r, theta, and phi, we can go for a surface for the system phi is equal to constant. Now when we take a phi is equal to constant, I'll get a surface like this. I'll get, this is for phi is equal to constant for this, and if this is connected here, you will get this to be a cone with its vertex at the origin. So for theta is equal to constant, we get this type of cone as shown in the diagram, and therefore from these given options, the coordinate surface is a cone with its vertex as origin, and that's what option A is the correct option for this question number 2. So you can understand how to draw a XYZ coordinate system, how to draw this R theta phi coordinate system, and how to go for different coordinate surfaces. Here theta is equal to constant is a cone. Now this is what, again I'll get R theta and phi, these are the new coordinates of this spherical polar coordinate system. When we go for R is equal to constant, then we will get a sphere of radius R. So when I go for this particular R is equal to constant, likewise that means theta is equal to constant is a cone, then R is equal to constant, it is a sphere, and this phi is equal to constant. For example, this phi is a constant, so we'll get a plane parallel to this z axis. So this is the plane which is said parallel to the z axis, so this is going to be plane. So here amongst these options given, if we want to a cone as a coordinate surface, in that case theta must be constant. If I want to be a sphere to be a coordinate surface, then R is going to be constant. If I want plane to be a coordinate surface, in that case this is going to be a this phi is equal to constant, and there is no question about this cylinder here, because this comes in the cylindrical coordinate system. So out of this given cone, sphere and plane, we can have these three different types of coordinate surfaces as shown. Next, in the spherical polar coordinate system, phi is equal to constant, coordinate surface is, now we have just now seen, and here the answer is C. It forms a plane which is parallel to the z axis, and that's what the question number 3 answer, correct answer is C, that is plane. In a spherical polar coordinate system, phi is equal to constant, the coordinate surface is a plane with its vertex at the origin. We have drawn the diagram on that, also we can go for that type of distinction. Then this problem is also related to the same one, same concept, that is in the spherical polar coordinate system. Now this time R is constant, so the coordinate surface is, this time it is going to be a sphere. So R is a sphere, so this is for theta is equal to constant, this is for R is equal to constant, and this is for phi is equal to constant. Remember, these three coordinates R, theta and phi, this decides what type of coordinate surfaces will be as per this discussion. Now another coordinate system, in cylindrical coordinate system, the coordinate surface phi is equal to 0 constant is dash dash with its axis parallel to the z axis. So again here we can draw a similar diagram what we have drawn earlier. So this is what your this is my x, then this is y, and this is z as well. Now let's take any of this point P here with coordinates x, y and z. Now this distance from this is going to be from z axis is given to be rho, then the angle made by this particular with this is given to be phi. Okay, I can take this to be x axis, no problem, this is y axis. So angle made by this projection of this rho on this particular surface, xy surface, or z is equal to 0 plane, is taken to be phi. And here in this there is rho, theta and phi. So these are the three different coordinates in case of spherical polar coordinate system. And let's see here when I go for these three different coordinates here, this is theta, in case of this cylindrical coordinate system, we have three coordinates. that is rho, phi and z. So this is z and this is phi and this is rho. So rho is the distance between the z axis and this point P, and if I draw a surface here for phi is equal to constant, I'll get a cylinder as shown by this. So when we draw this, we will get a phi is equal to constant is going to be a cylinder as shown by this particular diagram, and therefore for question number 5, D is the correct option. So here all the questions which we have discussed up till now, these are based upon the type of system and the coordinate surfaces as well as the coordinate planes and so on. In general, curvilinear coordinate system, the coordinate surfaces in general may be, okay, so this is what a curvilinear coordinate system. It cannot be linear all the time, it cannot be planar all the time, it must be curved. So all the surfaces, the curvilinear coordinates or as well as coordinate surfaces may be a curved one, and that's what this C is the correct option of this. You might have heard about this or seen earlier this diagram. So let there to be three different surfaces like this. So this is one curved surface where I have taken u1 is equal to 0. This is another curved surface, so here it is taken to be u2 is equal to 0, and this is the third surface which is where in taken we take its equation to be u3 is equal to 0, and therefore this is my u3 axis, then this is my u1 axis, and this is my u2 axis. So these three different axes u1, u2, u3 are curved one, and the surfaces here u1 is equal to 0, u2 is equal to 0, u3 is equal to 0 must be curved surfaces, and then such type of system is called as curvilinear coordinate system. Now for this system, whenever I can draw a tangent to this, these are called as unit vectors, and then we can go for its discussion later on. Now this is what question 6. So correct option of question 6 is C, that is curved surfaces. Now question 7. A coordinate system for which the tangent to the coordinate curve are dash dash to each other is called as orthogonal curvilinear coordinate system. The same diagram which I have drawn here, this is what one axis, this is the another axis or the direction, and this is third axis. So if I take this to be u1 is equal to u1, then this is u2 and this is u3. So this is the surface for which u2 is equal to 0. This is the surface for u1 is equal to 0, and this is the surface for u3 is equal to 0. So these are three different curved planes. u1 is equal to 0, u2 is equal to 0, u3 is equal to 0. These three curved planes, and they are intersecting each other in such a direction, in such a manner that I get the intersection of u1 is equal to 0 and u3 is equal to 0 gives me second direction, that is u2. Then u1 is equal to 0 and u2 is equal to 0 intersection gives me u3, say third direction, and similarly u2 is equal to 0 and u3 is equal to 0. This intersection gives me the third curve direction, that is given by u1, and here from this common intersection point I can draw one tangent there. So this is called as E2 cap. Then for this I can draw one tangent, so this will be E1, E3 cap, and similarly for this also I can draw another tangent, that is E1 cap. So all these tangents at one point, they will be found to be perpendicular to each other whenever for any curvilinear coordinate system these tangent drawn to the curved surfaces or this curvilinear lines, curvilinear axes, these tangents are found to be perpendicular to each other, mutually perpendicular, then such type of system is called as curvilinear coordinate system. Therefore correct option of this question number 7 is C, mutually perpendicular. So the coordinate system for which tangent to the coordinate curves are mutually perpendicular to each other is called as orthogonal coordinate system. On this particular definition, we are going to show that XYZ Cartesian coordinate system, XYZ or Cartesian coordinate system, R theta phi, that is the spherical polar coordinate system, and rho phi z, that is cylindrical coordinate system. All these three coordinate systems, their unit vectors are found to be perpendicular to each other, actually mutually perpendicular to each other. So all these systems are orthogonal coordinate system, and for a generalized curvilinear coordinate system, here also this property that shows that E1 cap dot E2 cap, E3 cap dot E1 cap. So whenever this type of dot product of any two unit vectors is obtained, it is found to be 0, means all these unit vectors are mutually perpendicular to each other, and therefore such a system is called as orthogonal curvilinear coordinate system. That is true for this ordinary coordinate system like XYZ Cartesian or this cylindrical, as well as it is true for this spherical coordinate system too. So this concept of orthogonality can be understood very easily once we go for this discussion of all these coordinate systems. Now next question, these are the geometrical elements as we have seen earlier. Question number 8, the volume element in the curvilinear coordinate system is given by. Remember, in curvilinear coordinate system we calculate h1, h2, h3 are the three scale factors, as well as we calculate du1, du2, or we take this du3 as the three differential directions or three differential length elements. Therefore length element in this system is given by h1 into h1 into du1 multiplied by h2 into du2, that is the surface element. In case of volume element, now there are product of this h1 du1, h2 du2, h3 du3. Therefore C is the correct answer of this question. So volume element has a product that is given by h1, h2, h3, and then finally du1, du2, du3. Because single length element is this, either in h1 u1 direction, u2 direction, or u3 direction, and product of all these three gives you volume in the curvilinear coordinate system. So it is a product of h1, h2, h3 and multiplied by du1, du2, du3. As usual, we know that we go for calculation of this h1 by root of g11, where this g11 is called as metric coefficient and this h1 is called as the scale factor. Now we know that how to calculate this h1 or g11 for any of the system. Now this, from this definition, GII, this scale, this metric coefficient is given to be daba Ri upon daba R, then daba R upon daba Ri, daba R by R bar upon daba R, and daba R bar upon daba R. Okay, so Rj, this is daba R bar. This is differentiation of vector with respect to scalar. We have to differentiate this vector R bar with respect to Rj, as well as differentiate this R bar with respect to Ri, and when I is equal to j, we can get this is like g11 or g22 or g33. These are the product of differentiation of vector with respect to scalar. So it is this is called as the partial differentiation, daba R bar upon daba R1 into daba R bar upon daba R1. So whenever this type of differentiation is obtained, it is a scalar product of these two vectors, then we get g11, and once we obtain this type of scale, this metric coefficient, we can obtain this h1, h2 as well as h3 from this simple definition. So h1 is given by root g11, that will be needed in the further discussions too. Now next, surface element in the curvilinear coordinate system in the xy plane is given by. So it is a xy plane. Now in the actually this is surface element in the curvilinear coordinate system. It is given by product of two sides or the two length elements. So you can go for either this in the xy plane. Okay, so we are asked this to be in xy plane. So it is, you have to take I am taking u1 to be x, u2 is taken to be y, and therefore in Cartesian coordinate system I get this ds is equal to dx into dy. Here dx is equal to h1 into du1 and dy is equal to h2 into du2. So taking this product, I'll get this differential surface element ds is equal to this product h1 into du1 into h2 into du2, and finally it is h1 h2 into du1 and du2. Other four options h2 h3, this is along z and y axis. h1 h3, this is along x and z axis, this is along x and y axis, and there is no such h4 is defined in this case of curvilinear coordinate system. So this option is completely wrong there. So either of this, you can go for this or this. All these are the surface elements in case of the curvilinear coordinate system. So different in the different directions you can go for this type of calculation. So in examination, maybe as part of xy plane, if you are asked xz plane, then go for correct options amongst all these three. Okay, so that is what question number 9. Now question number 10. In the spherical coordinates, what are the coordinates of the spherical coordinate system? And it's very simple, that is r coordinate, theta and phi. Two are the angular one and one is linear. So r, and we know that this r varies from 0 is less than or equal to r is less than or equal to infinity. So all positive. So r takes values all positive values. Theta varies from, so theta in this case varies from 0 to how much? So the theta varies from 0 to 90 degrees. Okay, 90 degrees. And this phi varies from 0 to twice pi. So both of these are angles, whereas this is going to be the it has dimensions of length, this has dimensions of the angle. So this is a coordinate system which is called as spherical polar coordinate system, and it has these three parameters or axis or coordinate axis, that is r axis, theta axis and phi axis, and therefore this particular coordinate system, the correct answer of this question number 10 is A, r, theta and phi. Now question number 11. Which of the following is called as a rectangular coordinate system? So that is a very simple question, it doesn't require any understanding. So spherical system is not, it is having three different that means one is r, second is theta and phi, so there is an angle. In the Cartesian, then cylindrical is also not the case, none of these. The correct answer of this question is this B, that is the Cartesian coordinate system is called as a rectangular Cartesian coordinate system. Okay, so we know that this is x, this is y and this is z axis. So all these three axes are perpendicular to each other. Their unit vectors are also found to be perpendicular to each other, that is small I cap, small j cap, small k cap. These three unit vectors are mutually perpendicular to each other. Such a system is called as a rectangular coordinate system, and therefore Cartesian coordinate system is also called as a rectangular coordinate system. That is very easy question, we should not go for more time about this. For this question number 12. If the three unit vectors of coordinate system are perpendicular to each other, then such a coordinate system is called as, just now we have drawn this diagram, we have shown this I cap, j cap as well as k cap. Go for any of the product I cap, j cap, that is going to be 0, or j cap dot k cap, that is also going to be 0, or k cap dot I cap, that is also going to be 0. So any coordinate system, this is what a Cartesian coordinate system where I cap, j cap, k cap are found to be such that their dot product with other vectors is always found to be 0. In case of spherical polar coordinate system, we have these three, er cap, then e theta cap as well as e phi cap. These are the three unit vectors we can see here in this system. Here also this er cap dot e theta cap that is can be shown to be found to be 0, or any other combination of the unit vectors is found to be 0. Same is the case for the cylindrical coordinate system also. Here also we have e rho cap, then e phi cap and e z cap. Here also product of any of these two is found to be equal to 0. So all such systems are called as orthogonal coordinate system, and therefore if the three unit vectors of coordinate system are perpendicular to each other, then such a coordinate system is called as orthogonal coordinate system. Hence B is the correct option for this question number 12. Okay, now let's go to this question number 13. You have seen question number 12. Question number 13. The tangent drawn to the coordinate lines at a point are called as coordinate axis, coordinate lines, coordinate surfaces, and D is the coordinate system. So from our definitions, it is very easy to answer this question. So tangent drawn to the coordinate lines at a point are called as coordinate axis. So question number 13, A is the correct answer given here. Now for orthogonal coordinate systems, the metric coefficients Gij is equal to 0, option A, Gij is equal to 0 if I is not equal to j, Gij is equal to 0 if I is equal to j, Gij is equal to 1 if I is not equal to j, and Gij is equal to 1 if I is equal to j. Out of this, option A is the correct option as we have defined just now. So this Gij is given by daba r bar upon daba ri dot daba r bar upon daba rj. Now provided in the orthogonal coordinate system or orthogonal coordinate system, this dot product of daba r bar upon daba ri and daba r bar upon daba rj, this is differentiation of vector r bar with scalar ri, differentiation of vector r bar with respect to scalar rj. This product must be equal to 0. So this will be possible only when I is not equal to j, and therefore this metric coefficient Gij will be equal to 0 provided I is not equal to j. Therefore this is the requirement of every orthogonal curvilinear coordinate system, and that is how when we go for G11, then we get daba r bar upon daba r1 dot daba r bar upon daba r1. So this dot product must not be equal to 0, it will have certain value, and we can calculate for either Cartesian coordinate system or any other type of coordinate system, such type of metric coefficient can be calculated, and from that metric coefficient we also calculate the scale factors with which following problem is there. So question number 14, correct answer is E. Now question 15, scale factors and metric coefficient for curvilinear coordinate system has following relationship. So this is again just now we have seen, this is what h1 is given by g11, h2 is given by g22, h3 is given by root of g33. So see here, this is option B is h1 is root of g12 h2, g12 root of g12, h3 is root of g23, h3 is root of g31. This is not correct. As well as h1 is equal to root of g13, h2 is equal to root g21, h3 is equal to root g33. This is also not correct, and this type of relationship is also not valid. So these scale factors and metric coefficients, these are connected by this h1 is equal to square root of g11. So from the first metric coefficient g11, we can get first scale factors. Similarly, taking square root of g22, we will get h2. From square root of g33, we will get h3. Therefore option A is the correct option for this question number 15. Now question 16, the Laplacian operator. Now this doesn't require whether you are working in any of the system or curvilinear coordinate system. Laplacian operator is always taken to be del square, and this is always, it is going to be a scalar operator. So in which system you are working in doesn't matter, all the time Laplacian operator is going to be a scalar operator. Therefore option A is the correct for this question number 16. Now the metric coefficient, question number 17, the metric coefficient for Cartesian coordinate systems are, okay, that is what we have just now seen. This scale metric coefficient G11, which is given by daba r bar upon daba r1 and multiplied by daba r bar upon daba r2, sorry, r1 again, but here r1 is nothing but x, r2 is equal to y, or r3 is equal to z. Some books use daba r bar upon daba u1. So u1 is equal to x, u2 is also equal to y, and u3 is equal to z. So either you can take r1, r2, r3, or you can take u1, u2, u3. But here this is nothing but daba r bar upon daba x as per the definition of the book. Then this is a product is given by daba r bar upon daba x dot daba r bar upon daba x. So our r bar is ix plus jy plus kz in Cartesian coordinate system. Now its differentiation with respect to first, that is x, is given simply I cap. Similarly, now differential of this and this with respect to x is 0 and 0. So and therefore getting this G11, I will get this is I cap dot I cap, and that is equal to 1. So hence I got G11 is equal to simply 1. Similarly, go for a calculation G22, that will give you dabba r bar upon dabba y dot dabba r bar upon dabba y. This is also j cap dot j cap, that is 1. And similarly we can go for third answer G33, that also will give you dabba r bar upon dabba z dot dabba r bar upon dabba z, that is simply equal to k bar cap dot k cap, that is equal to 1. And therefore C111, that is the correct answer for the question number 17. The metric coefficient of Cartesian coordinate system are simply 1, 1 and 1. So that can be obtained very easily. Now scale factors for cylindrical coordinate system. Now getting scale factors for cylindrical coordinate system, what we require is here we have to go for simple calculations. So scale factor is given, h1 is given by root of g11. Okay, we'll do one calculation, and here g11 in case of this cylindrical coordinate system, here rho, phi and z. So these are the three different types of coordinates used here. So that is to be obtained as dabba r bar upon dabba rho into dabba r bar upon dabba rho. For that, first we have to write this r bar vector in terms of its coordinates. So you have to use transformation equations to write this r bar in such a manner. And when these things are obtained, when we go for all these calculations, first g11 comes to be simply 1, and therefore this h1 in this case is square root of g11 is equal to 1. If I go for another calculation g22 in this case, since it is an orthogonal coordinate system, g22 will only appear. This, if it is calculated, it comes to be rho square, and therefore h2 is equal to simply root of g22, and this is simply rho. And similarly, third calculation g33 gives you again here to be 1, and therefore h3 is equal to root of g33, and if it is calculated, this is comes to be 1. So 1, rho and phi, these are the three different scale factors in terms of cylindrical coordinate system. So correct answer of this question number 18 is E. Now question number 19, identify the correct statement of the following. So 4 statements are given. Out of these we have to go for exact identification of the scale factors and metric coefficient of different types of coordinate system. So read statement 1 or A is the cylindrical and spherical polar coordinates have same scale factors. This is not true, because if it is the same, then systems will be the same. That is not true. The cylindrical and spherical polar coordinate systems have different scale factors. So this statement may also be true. Then let's check this. The metric coefficient of cylindrical and spherical coordinates are identical. This is also not true. And metric coefficient of cylindrical and Cartesian coordinate systems are different. Okay, so metric coefficient, that is g11, g22 and g33 for cylindrical as well as Cartesian, these must be equal to, must be different, otherwise again these systems will be true. Therefore correct answer of this particular question is this B. So both of these systems, cylindrical and spherical polar coordinate system, they have different scale factors. So h1, h2, h3. If we go for this cylindrical, it is given by what we go for h1, h2, h3 is given by 1, rho and 1 again for cylindrical, and for spherical again it is 1. Okay, we can calculate this, and that is again found to be different for this. So question number 19, correct answer is this question, that is option B. Given here this is not correct, so check this particular question at home when you go for study of all this. Now question number 20, the volume element in the curvilinear coordinate system is given by, again, so curvilinear coordinate system, as I said, this length element is given by h1 into du1, second is h2 into du2, third is h3 into du3. So product of all these three gives you h1, h2, h3 into du1, du2, du3. That is just a repetition of the earlier question, so we won't go for that. Then question number 21, the divergence of vector point function E bar. So divergence, again irrespective of the any coordinate system, what we are going to calculate or what we are going to use, del bar dot f bar, this is a dot product of two vectors, that is always going to be a scalar physical quantity. Therefore, divergence of vector point function a bar is always a scalar physical quantity, and therefore option B is the correct option for this question number 21. 22, scale factors and metric coefficient are identical. So go for studying all these type of systems. You will find that for Cartesian coordinate system, h1 is root of g11, and here this h1 actually g11 is equal to 1, therefore h1 is also equal to 1. This hg22 is equal to 1, and therefore h2 is also equal to 1. g33 is equal to 1, therefore h3 is also equal to 1. That means all these scale factors and these metric coefficients, these are found to be same for Cartesian coordinate system, and therefore correct option of this question number 22 is C, that is Cartesian coordinate system. Now question number 23, for Cartesian coordinate system, values of scale factors h1, h2, h3 are, this is again a simple, very simple question what we have discussed just now. Answer is D, that is 1 1 1. All these three scale factors are found to be 1 1 1 because their metric coefficient g11, g22, g33 are equal to 1 1 1, and therefore D is the correct answer for question number 23. Now question number 24, an infinitesimally small volume element in the spherical polar coordinate system and in the cylindrical coordinate system respectively can be taken as, this is again a memory question, so you have to go for this. dV for any of the curvilinear coordinate system is given by h1, h2, h3 into du1, du2 and du3. So use this formula to get, so here in both of the system, this is r into r sine theta and multiplied by, so 1 r and r sine theta, these are the three different types of h1, h2, h3 in case of the cylindrical spherical polar coordinate system, and multiplied by dr, d theta, d phi. This is the volume element in the spherical polar coordinate system. Similarly, 1 rho and 1, that product here also h1, h2, h3 is simply rho into d rho, d phi, dz. So this is the volume element in the cylindrical coordinate system. So out of given of these four options, option A is the correct. This is the volume element in spherical polar coordinate system, this is the volume element in the cylindrical coordinate system, and all other options given are not correct option, so you need not worry about this. So question number 24, A is the correct option that can be seen from this. Now scale factors for spherical polar coordinate system, as I said, this is what nothing but h1, h2 and h3. So these are obtained by taking so in this particular coordinate system, r theta phi, these are nothing but u1, u2 and u3. So using that particular factors, gij is equal to daba r bar upon daba u1 dot daba r bar upon daba u2. If I go for all these calculations, then I get gij is equal to 1, so square root of that is 1, that is g11, or then g22, that is going to be r square, and therefore h2 is equal to r, and g33 is equal to r square sine square theta, and therefore it is simply r sine theta. h3 is r sine theta. Therefore the scale factors for the spherical polar coordinate system is 1, r and r sine theta. So till now we have seen 1 1 1 are the scale factors for the Cartesian, then 1 rho and 1, these are the for cylindrical, and this is what just now 1 r and r sine theta, these are the scale factors for the spherical polar coordinate system. So just remember these three things. For Cartesian 1 1 1, for cylindrical only intermediate in between scale factor h2 is simply rho, otherwise it is 1 rho and 1, and for the third, that is spherical, also it is 1 r and r sine theta. So remember these 9 parameters, or amongst these three coordinate system, these three different types of scale factors, you will be at least 1 or 2 questions based upon this. So getting this is a mathematical one, but remembering this is not that difficult. You can go for that type of calculations. Now Let's come to this calculus part here. The gradient in the linear curvilinear coordinate system. Okay? So this should be curvilinear. There should be word curvilinear. Curvilinear coordinate system is given by, so this is what is given, E1 cap upon H1. So this is unit vector upon scale factor into partial differentiation with respect to first parameter dava upon dava U1 plus E2 cap upon H2 into dava by dava U2 plus E3 cap upon H3 into dava upon dava U3. This is the correct option. This is again a memory question. Remember, there is a vector, unit vector in 3 different directions. These are the scale factors in 3 different directions, and these are the partial derivatives with respect to first direction, second direction and third direction, and all other options. Option B, here doesn't come this E1 cap, E2 cap, E3 cap. So this is not going to be a gradient because it doesn't have any direction. Whereas there is a direction is provided by E1 cap, E2 cap, E3 cap. In the third option, E1 cap, E2 cap, E3 cap appears there, but the scale factors are appearing here H1, H2, here H2, H3 and here H3, H1. That is also not correct. So therefore this is also not correct answer. This is also not correct answer. This cannot be also, and therefore the correct answer of this question number 26 is A, that is E1 cap upon H1 into dava by dava U1 plus E2 cap upon H2 into dava upon dava U2, E3 cap upon H3 into dava upon dava U3. In Cartesian coordinate system, we have H1, H2, H3 is equal to 1, 1, 1. Then I have dava upon dava U1 is equal to dava by dava U1 is dava upon dava X. Similarly, dava upon dava U2 is equal to dava upon dava Y, and dava upon dava U3 is equal to dava upon dava Z. Then E1 cap is nothing but your unit vector I, E2 cap is unit vector J, and E3 cap is unit vector K. Therefore this gradient in case of this operator here, gradient operator del bar in this Cartesian coordinate system is given by I cap into dava upon dava X plus J cap into dava by dava Y plus K cap into dava upon dava Z. Here there is 1 is hidden, that is not needed to be written here. So this is what the gradient of this curvilinear coordinate system is defined by. This is gradient operator, of course. Del bar can be obtained by written by as this. It can be operated over the scalar point function as well as it can be operated the vector point function, and then we get gradient of the scalar point function. And vector operation is 2 different types, scalar multiplication as well as vector multiplication or cross multiplication, and that is what your divergence and curl of the vector field. Now next problem is related to this divergence of curvilinear coordinate system, which is given by this formula. Del bar dot f bar is equal to, see this product, 1 upon h1, h2, h3, all these 3 scalar product, scalar factor, this is the product of this. Then in the bracket dava upon dava u1, first bracket is f1, so first parameter of the vector point function into scale factors h2 and h3. Second term is dava upon dava u2 into the second parameter of f2, that is f, that is f2, into scale factors of first and third, that is h1, h3. Similarly, last term is dava upon dava u3 into f3, that is the third component of vector point function, into h1 and h2, which are the scale factors of first and second direction. So this is the definition, or this is the expression for the divergence of any of the vector point function in the curvilinear coordinate system. And as we know, divergence of vector point function is, since this is a dot product, it is always going to be a scalar quantity. Just to remember this, I have added this particular question here. Sometimes in examination you may be asked, different equations will be given. If this order is changed, h1 h2, then this is written to be h1 h2 and h1 h2 h3, then this h1 h3, like this. So minute change in one of the parameter if it is made, and if you are asked 4 such equations are given, and then you are asked write pick up the right equation or the correct equation expression for divergence of a curvilinear coordinate system, we should be able to go for this type of calculation. So writing this frequently and then trying to go for its variations, etc., that must be understood very easily when we go for this type of divergence of a vector point function in the curvilinear coordinate system. But remember, divergence of any vector point function in any of the coordinate system is always going to be a scalar. Therefore, question number 27, correct answer is this B. It is a scalar quantity. Now, this question is again exactly similar. This is Laplacian. Try to understand the difference between this and this. So this is our divergence. Laplacian is given to be del square. This operator Laplacian is given to be del square is equal to, again, 1 upon this product h1, h2, h3 scale factors. Then in the bracket dabba upon dabba u1, in the bracket scale factor of second and third direction divided by first direction h2, h3 upon h1 into dabba upon dabba u1. Second term and third term similarly can be written as. So writing this del square operator in any case is always very easy if it is this particular type of expression is seen. And remember, as we have said earlier, Laplacian of any of the scalar point function, vector point function, if it is obtained, this is always going to be a scalar physical quantity, because it is going to be a dot product of del bar dot del phi or del v. So whatever we will get, so that's what this particular answer of this question is again going to be a scalar quantity. So Laplacian is del square v, okay, is can be written as del bar v dot del bar dot v dot del bar v. Okay, so this not this, this is written del bar dot del bar v. This is a vector, this is also vector. Dot product of any two vector is always going to be a scalar. Therefore, this del square v vector point function is always written as a scalar physical quantity. That's what question number 28 is B. Correct answer is this. Now, writing curl of the vector point function in the curvilinear coordinate system, we come across this type of beautiful equation. Del bar cross f bar is given to be, again, this product 1 upon h1, h2, h3 scalar products, and the determinant is in the first row it is h1 e1 cap, h2 e2 cap, h3 e3 cap. Then the second row is partial differentiation with respect to first direction dabba upon dabba u1, partial differentiation of second direction dabba u2, and this is the partial differential with respect to third direction u3. Then this is component of f1, f2, f3, component of vector point function f1, f2, f3 multiplied by three respective scalar factors h1. So it is f1 h1, f2 h2 and f3 h3. And we know that since this is a cross product of two vectors, this quantity is always going to be a vector quantity, and therefore question number 29 correct answer is A. It is going to be a vector. So gradient is a vector, divergence is a scalar, and curl is also going to be a vector. So from the examination point of view, remember these three different definitions or the expressions for gradient, divergence and curl, provided you have a knowledge of the scalar triple product, you have a knowledge of all these three different types of coordinate system, scalar factor, their scalar factors, their metric coefficients, etc. that is known to you. And the last question here, that is for spherical polar coordinate system, which of the following is true? For spherical polar coordinate system, we have seen we have three different unit vectors, er cap, then e theta cap and e phi cap. Take any pair here, either er cap dot e theta cap, this is always going to be 0, or er cap into e phi cap, that is also going to be 0, or e theta cap dot e phi cap, that is also going to be 0. So this is correct, this is correct, this is also correct, and therefore all the options are correct, and that's what option D is the most correct option, that is found to be the correct for this spherical polar coordinate system. So that is how from this chapter number 1, try to write or to get the idea what are the three different types of coordinate systems, what are their different parameters, that means the three different axes. Based upon that, go for different calculations like h1, h2, h3. Before that, go for different calculations like metric coefficient g11, g22, g33 and the required conditions. Then once we go for all this h1, h2, h3 etc., then we can go for the unit vectors. Then it is very easy to write length element, surface element, volume element, as well as we can go for gradient, divergence and curl, provided we have knowledge how these quantities are defined in the curvilinear coordinate system. So defining is different and applying them for different types of coordinate system, that is different. So do all these things. This particular chapter is one of the very easy chapter to answer all its MCQ in the coming examination or the university examination. Okay, so that's what I conclude here for this particular chapter number 1. So thank you for patience listening. In the next video we will go for the chapter number 2, that is the special theory of relativity. So thank you all.